This is Chapter 5 summary. In this chapter, we will be covering temperature, thermal expansion, liquids and gases, thermodynamics, heat transfer, specific heat, phase transitions, humidity, heat engines, and heat movers. Let's begin. Temperature. Temperature is most commonly used physical quantity in our daily lives. Next to time. We might loosely define temperature as a measure of hotness or coldness, but this is rather vague and ambiguous because in the summer, 70 feels cold, while in the winter, 70 feels warm. So it's very vague, the heatness or coldness. But, and also it cannot be, it's not the same as heat or internal energy. For example, when one drop of hot coffee hits your finger, it may have the same temperature as sticking your finger in a whole cup of it, but that one drop has much less internal energy than all the hot coffee that your finger encounters when you place it in a cup of coffee. So it's not the same. But it can loosely be thought of the amount of kinetic energy in the molecules and atoms of a substance. There are three different scales. We have the Fahrenheit, the Celsius, and the Kelvin. And most of us are real familiar with Fahrenheit, especially if we have lived in in the USA for any amount of time. We are very familiar what an 80-degree day feels like, or what a 50-degree day feels like. So this is something we're very familiar of, but most of the world uses a different scale. They use what we call the Celsius scale. And this is pretty convenient because in this scale, water freezes at 0 degrees C. And in this scale, water boils at 100 degrees C. Whereas here, water freezes at, I believe it's 32 degrees F, and it boils, water boils, I guess 212 degrees F, if I'm not mistaken. All right, but the one that scientists love to use is called the Kelvin. And that's because, as it turns out, there is no upper bound to temperature, no upper bound. In other words, you can, as much energy as you want to get in, you can keep raising the temperature. But as it turns out, there is a lower bound. There is a lower bound. And this value is called absolute zero. And this is where you just can't get any lower than absolute zero. And why we love the Kelvin scale is because Kelvin, 0 is absolute zero. But at Celsius, it is actually a negative 273 degrees C. And the thing is, with the Kelvin and Celsius, they are basically the same scale. In other words, the size of 1 degree in each of these scales is the same. So the difference between 1 degree and 2 degrees is that same jump in Celsius and Kelvin is the same amount between each degree. It's the same. But what we do in Kelvin, whereas in Celsius, absolute zero is negative 273, in Kelvin, absolute zero is actually 0. And therefore, in Kelvin, water freezes at positive 273, and water boils at 373. And we're going to be using, and once again, it's K, and there's not that little degree thing in this. So we don't have that in the Kelvin scale, and K and K. So this is the one we're going to be using a lot in this class, the Kelvin scale. And there's a real interesting article in your book in the physics potpourri section called To Breathe or Not to Breathe. And I would like to encourage all of you guys to read it. And it talks about why certain planets have certain atmospheres. For example, on Earth, we don't have hydrogen in our atmosphere. And if you know anything about the periodic chart, if you've seen it, you know that the first and the lightest element is hydrogen. Hydrogen is the lightest element. It's got the least amount of protons and electrons in it. Anyway, in order for a planet to retain an atmosphere, it is a function of two things. It's a function of temperature and escape velocity, which is actually a function of the planet's gravity. So why temperature? Why temperature? Because as we discussed in the previous section, the temperature of a substance is proportional to the average kinetic energy of its molecules and atoms. And from the last chapter, we learned that energy kinetic is defined mathematically as 1/2 mv squared. So if I keep this term constant, if I hold this term constant, and my variables will be the mass and velocity. Well, as my mass gets smaller, then my velocity goes up as the square. So hydrogen at a certain temperature is going to have a much faster velocity than, say, uranium, because uranium is a much heavier element. So hydrogen at the same temperature as uranium is going to have a more vibrate or move more rapidly. It's going to have a higher velocity than the uranium will. All the elements, the lighter elements, are going to have a higher velocity. And the escape velocity is if I am, for example, if I throw a ball up and it'll come back down, right? Until I can throw it up so hard and so fast that it will leave the gravity. It will have enough energy to escape the Earth's gravitational pull. So that's what happened with all the lower elements. They achieved a temperature which gave them that escape velocity. And I'm not sure what it is on Earth. I think it's somewhere around the neighborhood of 25,000 miles per hour. But yeah, so that's a very good read, and it's in the physics potpourri. It's called To Breathe or Not Breathe. So we don't have any of the lighter elements in our atmosphere because they've all, at one time or another, achieved that escape velocity when temperatures got very high. All right, so that's a good thing to read. I encourage everybody to read that. It's just very interesting. Now, section 5.2 is thermal expansion. Okay, so thermal expansion occurs on pretty much everything. When it gets hot and cold, under hotter conditions, it gets larger. Under colder condition, it contracts. And our formula for that is delta L, the amount of length contraction. And we only have to do it in one dimension. We can, it's going to be the same in all three dimensions. So we only need one dimension to determine what it's going to be in any dimension, right? So our change in length is going to be equal to alpha. And alpha is called the coefficient of thermal expansion. Alpha is the coefficient of thermal All right, and that value is unique to each substance. If you look at table 5.2, we have some coefficients of linear expansion, and we have them listed for solid, brass, brick, copper, glass, bunch of things. And so once again, getting back here, it's delta L, the change in length, is going to be equal to alpha times the original length. That makes sense, right? The bigger it is, the bigger the change. The smaller it is, the smaller the change. And then finally times delta T, or the amount of change in heat or temperature, right? So this is our equation. So our thermal expansion in one dimension is going to be delta L equals alpha. L, and once again, L is the original length. And finally, delta T, or our change in temperature. This actually is used in thermometers, where you have, the thermometers with the red fluid in there. It's actually dyed red alcohol. And it expands, that's known. So they just mark it off with the degrees on the thermometer, and it expands according to the amount of heat. So we use it there. We also use it in things called bimetallic strips, which are used to make thermostats. So where you have two substances, two metals glued together here. One has a higher coefficient of linear expansion. So for example, say this one. So, and you've got like a pinned thing here. This will be your dial. When it contracts, it will look something like this, right? This is going to, the bottom part is going to contract more than the upper part, causing this thing to do this and maybe move down like that. When it expands, the bottom part will expand more than the upper part, causing the dial here to go move that way. And it's calibrated. So this is how your thermostats work. Another thing to note is that when engineers make bridges, they have to make these kind of expansion joints, right? And they're like this. Little fingers, interlocking fingers, right? And I guess in my house here in the desert, I have cracks in my driveway because the engineers did not put expansion joints in, and it expanded too far and therefore cracked. So make sure when you get some concrete poured, if you're in an area that like I live in here where we have a wild variations in temperature, they put those expansion joints in there, or else you're gonna have cracks in your driveway like I do. Okay. Liquids also expand and contract, and we've talked about how a thermometer, mercury works this way as well. Mercury thermometer, or one of the red alcohol thermometers work that way. Let's see, water is an unusual substance, and its density in the solid phase is less than its density in the liquid phase, which is really cool, and it helps life on Earth, because if it were more dense in the solid phase, when lakes iced over, the ice would sink and the water would be on top, and that wouldn't be very good for our marine life down below. So this lets fish and other life forms survive in sub-freezing temperatures, because they still have the ice on top, but their water is still flowing down below. So this is a good thing. Gases expand as well. And a very general equation for it is PV equals a constant times T. So the pressure and the volume equal some constant, a function of the gas, times the temperature. The temperature gets larger, then one of these have to get larger. Or one of these get larger, then the temperature gets larger. We can see this in a hot air balloon. All right, it stays inflated. The air inside is hotter than the ambient air. The pressure gets really great, which makes it inflate. All right, thermodynamics, section 5.3. Now we'd like to know how the temperature is changed. And there are two general ways to increase temperature. One is by exposing it to something that has a higher temperature. By exposing how do we change the temperature of a substance? By exposing it to something that has a higher temperature. And the second way is by doing work on it, by performing work on it. For example, you can put a pan on a hot stove, and in short order, it will increase. And another example of raising a temperature by doing work is by compressing a gas. When a gas is squeezed quickly into a smaller volume, its temperature increases. We want to know the definition for internal energy. And that is the sum of all the kinetic energies and potential energies of all the atoms and molecules of a substance. So the sum of the kinetic and potential energies of all the atoms and molecules of a substance. All right. And heat. Heat is the form of energy transferred between two substances when they have different temperatures. All right. The first law of thermodynamics says that the change in internal energy of a substance, so delta U, we'll call U the internal energy of a substance, is equal to the work done on it plus the heat added. All right, so delta U equals work plus heat. Section 5.4 is heat transfer. And there are three different mechanisms that we would like to learn: convection, conduction, I'll start with conduction, convection, and radiation. Convection is the transfer of heat between atoms and molecules in direct contact. Okay, and this is like our other example. You put a pan on a stove and it gets hot because you've got atoms and molecules in direct contact. You put your soup in that pan and that gets hot because the pan is hot. That is conduction. Convection is the transfer of heat by the buoyant mixing of a fluid. And this is an example of this would be you have a radiator in the room and you've got the hot air rises or sea breezes. So steady winds blowing into a shore along coasts are caused by convection. The sunshine warms the land more than the sea, so the air over the ground is heated and rises. Now the sea breeze rushes in to take its place. And finally, we have radiation, which is the transfer of heat by means of electromagnetic waves. And this is what we receive from the sun every day. The electromagnetic rays radiate from the sun and strike the surface of Earth and heat it up. And so this is radiation. Three different means of heat transfer. These two require a medium. They require an actual thing to transfer the heat. This guy can transfer it through a vacuum. So this requires a medium, and this can work in a vacuum. These two cannot work in a vacuum. All right. All right, section 5.5. This is on specific heat. Okay. Okay, so when I want to heat a substance up, all substances absorb heat at different rates. And that rate is called the specific heat. It's denoted by this small case c, and it's defined as the amount of heat energy, and that's Q, required to raise a unit mass of a substance by 1 degree C, or just call it delta T, and it's in degrees C, not F. So if you check out table 5.3, you've got specific heat capacities of a bunch of things. We've got aluminum, concrete, copper, ice, iron and steel, lead, silver, gas, mercury, seawater, and water. And if you look at this list, the one with the highest specific heat, which is at 4,180 joules per kilogram degrees C. That is the highest on that list. So water is very thermically stable. It doesn't change its temperature that easily, which in as much as we are on Earth is covered with water. We are made largely of water. That is a really good thing. That keeps our Earth thermically stable, and it keeps our bodies thermically stable. So everything else, the next thing is seawater, which is 3,900, but everything else is less than half of that. So water has a very high specific heat. That means it takes a lot of heat energy to raise its temperature. It wants to stay stable. It doesn't want to fluctuate up and down. What is a low one is copper. Copper is 390 Cu. Specific heat of copper is 390 joules per kilogram degree C. So, you don't want to hold that copper bar in the campfire too long. It's going to burn your hand. All right, that's specific heat. And this Q, by the way, Q is, big Q is the symbol we use for heat energy. It's got units of joules. Specific heat has units of joules per kilogram degree C. That's specific heat. Another interesting thing, or something you should take note of, many of the problems want to know how much heat is required to do some task. And this quantity is oftentimes rewritten as CM delta T, right? It's hard to actually measure heat quantity directly, and oftentimes we solve problems by using these as a substitute for Q. So please make a note of that. That will come in handy in your problem solving. Section 5.6 talks about phase transitions. And I have reproduced the chart on page 201. This is the phase transition chart of water. And this is Q added right here. So what I'm doing here is I'm adding heat. I'm starting, and this is temperature. Degrees C. All right, so what I'm doing here is adding heat steadily. I'm adding a steady amount of heat, and I'm starting at -25. So what happens here is I add heat and at -25, and my temperature raises until it gets to 0. And at -25, water is ice. So I'm raising the temperature of ice until I get to 0. At 0, I'm still adding heat, but the temperature is not raising. What's happening is a process called, well, we're melting the ice here. So right here, my ice is melting. And we call this phase, or this property, or this condition, the latent heat of fusion. So I have to add a lot of heat to melt that ice. So the amount I need to add here is 3.34 times 10 to the 5th joules per kilogram. So note there's no term like we had for the specific heat for degrees C in the denominator. I'm not changing the temperature. All I'm doing is changing the phase of that ice. So once all my ice is melted here, I'm adding my heat and I'm steadily raising my temperature. And that amount is 4,186 joules per kilogram degrees C. So for every 4,186 joules I add to each kilogram, I'm raising the temperature of water 1 degree C. And it's important to note that if I want to lower the temperature, I will get that same amount of heat back. Now, once I've gotten to 100 degrees, I'm still adding heat, but I'm not raising the temperature anymore. I'm boiling it off. So I'm going from that liquid state to the vapor state. And that requires even more heat than the latent heat of fusion. That would be 2.26 times 10 to the 6. Note that that's a full order of magnitude more. Joules per kilogram. So actually, when you're boiling that water off, you're actually having to do a lot more work because you're breaking the bonds of the liquid and actually fighting the gravity and raising it up and turning it to steam. Once it's all boiled away, then I add heat and my temperature rises steadily again. So this is the phase transition of water. It's good to know this chart, probably learn this chart, become familiar with it. We'll use it to solve a lot of problems in this class. Now we'd like to talk about humidity. All right, let me just read from the book. It says, at temperatures below their boiling points, liquids can gradually go into the gas phase through a process known as evaporation. So it occurs with evaporation. And humidity is a measure of the amount of water vapor in the air. Okay, and the important thing to know about humidity, we would like to know what relative humidity is. And I'm pretty sure you've probably heard this term on the news, the relative humidity. Well, what it is, it's the ratio of the actual humidity to the maximum possible times 100. And the maximum possible is called the saturation density. That would be a function of the temperature. The higher the temperature, the more water vapor the air can hold. So in table 5.5 on page 202, you will see the saturation density for a number of temperatures. And they're all in, well, you have the Celsius and the Fahrenheit. So you'll see the maximum amount of humidity the water can hold. And we'll do a few problems involving the relative humidity. So what it is the actual humidity divided by this maximum possible, or the saturation density, times 100. So yeah. And then when you hear that on the news from now on, you'll know what they're talking about. It's going to be awesome. The last two topics we will cover are heat engines and heat movers. Heat engines. Heat engines are your typical coal-burning power plant, your car engine, your nuclear power plant, anything that takes heat and converts it to steam and uses that steam to turn a turbine. You have a wonderful diagram, figure 5.37 in your book, of a heat engine. But basically what it does is it takes a hot steam, sends it up, uses it to turn a turbine, which turns a generator, which brings power to our lovely homes. And, makes us cool in the summer, keeps us hot in the winter, turns our lights on, and brings us TV. Then once the heat is used to turn the generator, the steam comes down to a cold reservoir, where it goes back to your heat flame, and it's just kind of recycled. But the thing to know about this is something called the Carnot efficiency. And it's named after some man, Carnot. I don't know his first name, but he was the one who came up with this. And anyway, efficiency, what efficiency is the power you get out compared to the power you put into it. I mean, nothing is 100% efficient. There's always losses, right? So what Carnot said, that we're going to use that temperature differential to give us the efficiency, because we're going to assume that all of that heat lost when the steam goes to turn the generator will be used to make power. Now we know that's not true, but the Carnot efficiency, I-C-I-E-N-C-Y, right? Sorry. Oh, I-E-N-C-Y, sorry. There. E-F-F-I-C-I-E-N-C-Y, or there we go. Anyway, I digress. The Carnot efficiency is the maximum possible efficiency of a heat engine. And it is the temperature high minus the temperature low. That's that temperature differential that we use to do work. So that's the work done, or the energy out. And then the temperature hot is the energy that we have to put into it. So this is our power out over power in times 100. And that gives us our maximum possible efficiency, or what we call our Carnot efficiency. And that's a heat engine. And the final topic we want to discuss in chapter 5 is our heat movers. And this is something like your AC or your refrigerator. You know, your refrigerator does not really pump cold air into your refrigerator. I know it feels like it does when you open the freezer door and you get barraged by that wall of cold air, but it doesn't really There's nothing pumping cold air in. What it's doing is it's using a refrigerant to extract the heat. So how does that work? Well, what happens is you've got, remember when you pump a gas and put it under high pressure, it increases the temperature. You've got some kind of compressor here. And this is high pressure right here, IP. And you're gonna have like what's called an expansion valve. And this is kind of like your deodorant, right? You spray your deodorant under your arm and it's real cold, right? If you ever have used spray deodorant. But you know that it's not sitting in your refrigerator getting cold. So why does your arm feel cold? Because that gas is there under a high pressure. And when it comes out, it releases all that energy and it wants to take energy from its surroundings. So that's what happens. That high pressure refrigerant is sent through that expansion valve. It expands, it releases its energy. It wants to suck up the energy from its surroundings. So that's what it does. And it takes all that hot energy from inside the refrigerator. And then it goes back behind your refrigerator. And I don't know if you've ever looked back there, but you've got those heat sinks, those coils, black coils like that. You ever stick your hand back there, you'll find that it's pretty hot. And that's where, excuse me, the heat from your refrigerator goes. And this is a closed process, you know, because we don't want that refrigerant contaminating our wonderful atmosphere. So this, that's how your refrigerators, your ACs work, so on and so forth. And that concludes chapter 5. This is your chapter 5 summary. So maybe listen to this, get to know this, perhaps, you know, do the problems. Anyway, thank you for listening.